Okay, today we're going to talk about chemical equilibrium, and what we really see here is that all reactions do not necessarily go to completion. So equilibrium, it's a concept, a chemical principle where we talk about a chemical reaction occurs not only in the forward direction, but also in a reverse direction. And the important thing to remember here is that it occurs when the forward reaction is happening at the same rate as the reverse direction or reaction. It's not that you have the same amounts, it's that they're occurring at the same rates. So that's the important part right there. And since you're getting both products and reactants that are constantly forming, it doesn't mean that nothing's going on. It's still a very dynamic system. There's lots of things going on. You're getting reactants formed and products formed at the same time. But to the naked eye, it might look like there's nothing really going on. You might not see anything going on in the beaker once the reaction has reached equilibrium. So again, here we're saying that chemical equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction. And then notice the arrow right here. This is how we illustrate that it's a reversible reaction. You have a two-sided arrow. This is just a little example showing some molecules. As time goes on, you can see that we have a lot of this NO2 that exists here. Well, we start getting some of these N2O4 molecules forming. Eventually, these remain constant. I've got 3 of those molecules compared to 4 of my NO2s. So it has now remained constant. It's not changing. So that means that we've actually reached equilibrium when there is no longer any change in concentration. But does that mean that reactant stops forming products? No, we can see that there's constantly changing of these positions within these diagrams here. So it's constantly going on. It's a dynamic process. And here's just a little graph showing what you would expect to see. Once you get it to the point where you've got this line flattens out and this line flattens out, right here there is no change in concentration anymore. So equilibrium has been reached when there is no longer any change in concentration. Okay, so back to your notes. Because a chemical system reaches equilibrium, the concentrations of all species remain constant. The ratio of the products to reactants will also be constant. So this constant is going to remain that constant regardless of what type of concentrations you throw in there. That's the constant. However, it does change based on temperatures. So just realize that you'll see temperatures thrown into the problems. So when we talk about calculating an equilibrium constant, and actually one of the first things we'll do is calculate an equilibrium constant expression, we're going to use this formula that we see right here. We've got this reversible reaction, so we've got a double-sided arrow, and these W, X, Y, and Z are coefficients. So when we calculate K, what you should really be noticing here is that C and D, those are our products. So we have products raised to the power of their coefficients divided by reactants raised to the power of their coefficients. So products go on top. And to give us a little bit more background about what we mean by products and reactants, we're talking about concentrations. So we saw this just last unit with the Nernst equation. We saw that whenever you see brackets, that's going to talk about concentration. More specifically, it refers to molarity. And you know, you guys had an example or two where you had more than one concentration in the numerator or denominator. So remember, that means that those values are multiplied. Don't make that common mistake of trying to add something like that. You will get the wrong value if you do it that way. So it's a multiplication that goes between the concentrations if you have more than one reactant or more than one product concentration. And then when we talk about concentrations, think about the types of things that have concentrations. A solid is just a pure solid. A liquid is just a pure liquid. So those do not have concentrations. However, if we're talking about something like a gas, well, those molecules can be close together or far apart, so you can have varying concentrations there. Or if you have a solution, you can have a lot of solute, you can have a little bit of solute. So aqueous substances also have concentrations, which means we do not put solids or liquids into our equilibrium constant expression. And let's see, reading this last one, it's just going through how you go about the formula there. It's going to be, again, it's your products, the concentration of your products raised to the power of their coefficients, divided by the concentration of your reactants raised to the power of their coefficients. So now we have, I'm going to skip this one. This is just really kind of like that the first couple slides I showed, where you can see things going on, some changes, and when has equilibrium been reached? Well, again, it's going to be when the concentrations do not change. So the rate that your reactants are being produced is equal to the rate that your products are being produced. Okay, so now we come to our first example, and I just rewrote our formula for our equilibrium constant up there. And it says write the equilibrium constant expressions. So when you see that word, that means you're not actually going through any calculations. You're just setting it up to see how you would then plug in some values if you had some numbers to play with. So here we're going to say that our product concentration, well, I look to my products and I have barium carbonate and some phosphate ions. Barium carbonate is a solid that has no concentration. So I'm going to start off by saying that K, and sometimes you'll see it written as KEQ, so your equilibrium constant is going to be equal to the concentration of your products, so that's going to be PO4 minus 3, in other words, your phosphate ions, and those will be raised to the second power because of your coefficient of 2. And we're going to divide that by the concentration of our reactants. So we look back at our reactants and we see that we have a solid here. Nope, solids don't have concentration, so we're not going to put that into our equilibrium constant expression. Instead, we put our carbonate ions only. And, sorry, there's a minus 2. And we raise this to the power of the coefficient that's in front, so raise it to the power of a 3. So that would be the equilibrium constant expression. You don't have any numbers to be able to throw in there, but you have set up the formula for it. Okay, next couple. Here, I'm just going to immediately go through and say solid, no, aqueous is good, aqueous, gas, solid, so we can cancel those things out right away. When we come here, we can say K, or KEQ, is equal to the concentration of your products, so that's going to be hydrogen gas. Concentration is symbolized with brackets, so I have to make sure I put those brackets in there, because that means the molarity of my hydrogen gas. I don't know what that is, but that's what would be plugged in there. And I'm going to raise that to the power of its coefficient, which is just a 1. If you want, you can throw that in there. I'm going to do it just for illustrating purposes here, just to make sure you know that we're thinking about it. And then we're going to divide that by the concentration of our reactants. We have hydrogen ions, and we would raise that to the power of 2. And we also have chloride ions that we would raise to the power of 2. And again, make sure you realize that what's going on here, and you don't have to draw this, but what's going on here is that you're multiplying those concentrations together. You are not adding them. Do not add those concentrations. You're multiplying. Or so you can plug that information into your calculator if you had values. Okay, last one that we have on this side of the paper. No, that's not true. Last one in example 1. We have I'm going to read through here. I've got a liquid, I've got a gas, and I've got a liquid. So when I do my equilibrium constant expression, it's just going to be my carbon dioxide gas concentration raised to the power of 12 divided by my oxygen gas concentration raised to the power of 15. So you now know how to write an equilibrium constant expression. Well, what can we do with this? We can actually plug some numbers in if we're given that information. So we read through here, we see our reaction, and it says that a quantity of PCl5 was introduced to a closed 12-liter vessel and heated to 250 degrees until the above equilibrium was reached. At that time, the vessel contained 0.21 moles of PCl5, you have your moles of PCl3, and your moles of Cl2. So calculate K for the equilibrium at 250 degrees. So the first thing I'm going to make a note of here is that we've got some information about our temperatures. We don't really care. This is not part of our calculations. However, with that said, this is just a reminder, this is something you should know, is that your equilibrium constant, K, changes with temperature. So if your temperature changes, then your K value is also going to change. So this is just illustrating that it's at a constant temperature, and this is what it happens to be at this temperature, but I'm not going to use that in my problem. So now I remember I'm going to be doing my product concentration over my reactant concentration, but I don't have concentrations. Instead, I'm given the size, the volume of my container, and I'm also given moles for each of these substances. But we're pretty smart. We know that concentration molarity equals moles per liter, so we can easily find this information. The way I'm going to plug this in now, I'm not going to use a calculator. I'm just going to go ahead and kind of throw it all out there, and then we'll get a number, a value. So we're going to do the equilibrium constant expression. We know gas, 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 so all of these are involved in our equilibrium constant expression. I'm going to take the molarity of my PCl3 raised to the first power times the molarity of my Cl2 raised to the first power, and then divide that by the molarity of my PCl5 raised to the first power. Then, maybe you would do this in your calculator, but I'm just going to write it all out to show what we're doing. The molarity of your PCl3 is going to be equal to the moles of your PCl3, so that's the 0.32, right? Hold on, yeah, 0.32 moles per 12 liters. So now you've got that as molarity once you throw that in there, once you calculate that. And that's raised to the first power divided by, times, we do the same thing for our Cl2. And then we are going to divide that by the concentration of our PCl5, which is 0.21 moles in that 12 liters. So when you do all of that math, you end up with 0.0406. Notice there are no units for your K value. It's just that number. There's no units to use. What we're going to see in the next video, and I'm not going to do this right now, well, you guys can think about this. If we know that K equals the product's concentration divided by the reactant's concentration raised to the power of their coefficients. So if you've got products in your numerator and reactants in your denominator, if you have a K value that's less than 1, what do you think that means? Do you have more of the stuff that's in your numerator or more of the stuff that's in your denominator? And if you're saying denominator, then you get the gold star because you're right. It means that we have a lot of stuff, a higher concentration of our reactants. So what this means is that this reaction happens to be favoring the reactants. So reactants are favored because we have a higher concentration in our denominator, if you think about that formula that we just looked at.